Hello, everyone. I'm glad to see you at the current iteration of Journal Club, and today we'll discuss the thesis topic with Kerven. Hello, Kerven. Kerven is a student of MSAI program, so Modern State of Artificial Intelligence at MIPT. And his thesis project is dedicated to EEG signals analysis and prediction. And today he will tell us about one approach to such time series, which is called Riemannian geometry, and present practical cases of that. As I said in the announcement, this is the first time Journal Club in English, but I think this won't be the last. And by the way, for students of MSAI and for students from MIPT, it's a great opportunity to present your job, your works to public. So don't hesitate to write to messages to me. And I think that's all I wanted to say as introduction. So Kerven, I think you are able to share the screen and slides, and
okay,
the word goes to you.
Okay, hello everyone. Thank you, Vladslav. As Vladslav said that, I'm second year student of Modern State Artificial Intelligence program. This work is mainly work prepared with Vladslav Goncharenko and Alina Samokhina. I mean, they are masters of this topic. If you want to focus mainly, deeply on these topics, you can contact them. And today I want to present this topic. I have some additional stuff to say about this topic. Okay, then let's start. The topic is Romanian geometry for time series. This is our outline. In the first part, I will introduce you about some introduction to the time series. I will give some explanation, some definitions about them, and we will talk about EEG signals and some problems like classification and forecasting problems. And then in the second part, we will move on to the Romanian geometry. We will talk we will look a general overview of Romanian geometry. We will make just some introduction to this topic. It's a huge topic. And in the third part, we will focus on the PyRiemann library. This library is using the, as you can see from the name, it is using the Riemannian geometry as a baseline. The final part, we will give some examples, some works which use it, this Romanian geometry. So, by the way, during the presentation, if you have any questions, you can ask me. I will try to answer on my base knowledge. So let's start with time series. Okay, what's a time series? First of all, the time series is also a data set, but it is just a second. But it is ordered in the time. I mean, for example, like sales history. These are the examples of some examples of time series. For example, monitoring of equipment. I mean, the main point is it should be ordered in time and a data set, but ordered in time. Okay, and the time series have mainly two classes. The first one is forecasting. Just a second. The first one is forecasting. This is just making a prediction based on your previous history. For example, the weather forecasting and any prediction based on your history. The first problem is forecasting, and the second one is classification. Mainly, our work of today is based on this classification. We want to classify our signals. Okay, then let's move on. Now let me introduce you the EEG data. It is data which is taken from our brain. It detects the electrical activity on your brain with these electrodes. As you can see in the. By the way, you can see my mouse, right? In the screen. Okay, thank you.
Yeah.
Okay. For example, in this way, it has some methods to take the signals. For example, in the right picture, it is called the 1020 international format of taking the signals. For example, we are putting electrodes in these points, these channels, and we are taking the signals from these points with these electrodes. Okay. Where can we use these signals? How can in which areas in real life it's used? The first one is brain-computer interface. This link is clickable. It is a YouTube video. If you want watch it, we will publish this slides. You can watch it. It is, for example, it is used for disabled people which cannot speak. The signals, EEG signals, are taken from our brain, and it is predicting how which words this person is trying to say. And this is a beautiful video. You can watch it from that. And for example, in the second case, it's used on the medical diagnosis. For example, it's based on it's used for predicting this Alzheimer's disease. It can, as I remember, it can predict before, for example, a lot of time ago, for example, 5 or 10 years ago, before the this disease is occurred in the people. Okay, as a last part, of course, there are so many other areas which is used this EEG signal, and as an example, the next one is games. You can play the games with just your EEG signals, the EEG signals from taking your brain. Okay, so let's move on. Now, classification. Our main task for this classification is ERP concept. ERP is, for example, we have a stimuli. For example, this video is stimuli, the right one. We are focusing, for example, age, and when this square is come to the age, there is a response in our brain, and our task is that we have a brain signals, EEG signals, and our task is predict this classify these signals. It does it have a target? I mean, does it have response or not? Okay. Mainly, for example, in this case, our task is classify these signals. Does it have target? Is it a target signal or non-target signals? Okay. First of all, by the way, let me introduce these terms. For example, we have EEG signals, and we are first term is epoch. Epoch is a time slot which is taken. For example, in that case, we have from 0.7 seconds, and target is, do we have a response? For example, this signal, a bit green one. In that case, we have a response to the stimuli. But in this signal, in the blue one, we don't have any response. It is a non-target signal. And this one, the green one, is target signal. Okay. So our goal is to distinguish these two signals, target and non-target signals. So now let's start with some math. We have, as we said before, we have signals, and we will write it in the matrix form. This is our X is our EEG signal, and these X1, X2, and Xn are the epochs. For example, in that case, we have n epochs. Okay, and our each Xi matrix is in that form. For example, this first form is a signal from these electrodes. In that case, because we have E rows, which means we have E electrodes in our brain, and each row is a signal on time points, sample time points from our electrodes. We have T1, T2, and TE signals. Okay, and as totally Xi is just an epoch which is taken from our brain, and our goal is to classify these Xis. I mean, these epochs. Does this epoch have target? Is this epoch is target or non-target? Okay, now let's introduce the covariance of this epoch. Okay, to start, before starting with the Riemannian geometry, let me introduce the covariance matrix, because before starting with it, we are constructing the covariance matrix of our epoch, our Xi matrix. The covariance matrix is built in that form. In the main diagonal, we have variances of these signals. I mean, signals from each electrode, and the other elements are, as you can see here, the covariance of these signals, and the covariance is measures how vary these signals, and it's calculated with this formula. It is estimated with this formula. For example, variance is estimated with this formula, and covariance between X and Y is calculated with this formula. N is the number of samples in here. Okay, then let's move on. Okay, now we introduce what is the EEG signals, and we take the covariance matrix of our epoch, our EEG signal in one specific time, in one epoch. Now let's move on to Riemannian geometry. Then we will learn how relate these EEG signals and Riemannian geometry relation between these topics. Okay, first of all, let me briefly introduce what is the Riemannian geometry. Riemannian geometry is a branch of differential geometry. We have these manifolds, Riemannian manifolds, and you can think it as I mentioned in here. You can think about like surfaces in a 3D, but our Riemannian geometry manifolds is in a higher dimension, but if you think about the 3D, three-dimensional, it is surfaces like that. These are the manifolds in higher dimension. It's a smooth like surfaces. And we have a tangent space in each point. The tangent space is a general form of the tangent plane. In the 3D, it's the tangent plane. For each point of manifold, we have a tangent space. And this tangent space have a inner product. I mean, not all the space are inner product, but this tangent space of Riemannian geometry have the inner product property in equipped. I mean, in mathematical term, it is equipped with inner product. So the overview about the Riemannian geometry is like this. And okay, why we are taking this Riemannian geometry for our task? Because this symmetric positive definite matrix is make a manifold. All this in the same dimension, all the SPD matrices are make a manifold. And as I mentioned here, we are taking the covariance matrix of our data, and these covariance matrices are the symmetric positive definite matrices. These covariance matrices are SPD matrices. That's why the covariance matrix make a manifold of Riemannian geometry. Okay, how properties of this manifold, how we are using these manifolds. The manifold, for example, any point, as I said, this CI is our, for example, covariance matrix. We have, and as I mentioned before, we have n epochs, and for each epoch we take covariance matrix, and this covariance matrix make a manifold, as you can see here. And in these manifolds, we have our covariance matrix. Then we can, on the Riemannian geometry, we can project this covariance matrix to the tangent plane, I mean the tangent space. We can, as a result, we can take the vector form of our covariance matrices. Okay, these are the how can we project it? To project this covariance matrix to the tangent place, first we are finding this reference point C. And how can we find this reference point? We will find reference point in that form. Okay, first of all, I will introduce you how we are finding it. First of all, if we have a reference point in our manifold, then we can project our covariance matrix to the tangent space with these formulas. For example, our CI is equal to SI can be found in that formula. Okay, the proof or detailed explanation can be found in these links. Okay, you can find a detailed explanation from there. I just put in our slide just the formula. By using this second formula, SI is equal to we are using the reference point and our CI. I mean, in the basic words, we are just converting our covariance matrix to the vector form SI into the tangent plane. Okay, how can first of all, now how can you find this reference point? This reference point is a solution of this equation. It is an arc minimum of this equation. This equation is sum of distances to each, the distance is geodesic distance, Romanian distance. We want to this distance minimum, sum of this distance minimum. The geodesic distance is the shortest way along the manifold from C to Ci, and we want to the minimum of this sum. And as a solution of this equation, we will get the reference point. Actually, there are other distances, not just not just a geodesic distance. I mean, not just the Riemannian distance. We have a lot of distance like Euclidean distance, log determinant distance, Western distance, and with these distances we can find the reference points with these formulas. But for the classification task, the best one is this geodesic distance. I mean, the Riemannian distance and Riemannian mean. And it's very deeply explained in this link, in these experiments. And as a result of this experiment, you can click it in here. As a result of this experiment, it is shown that the best one is this Riemannian geodesic distance for the classification task. Okay, so what's so far? Okay, what we did the project, we projected our covariance matrix to the tangent plane, and so what is our result? And after we projected this our covariance matrix, we will get vector form of our initial EEG signals. I mean, we get our epoch of EEG signals, and we make covariance matrix of this one. We found
Kerven, you are freezing sometimes.
Okay, just a second. Ska saati tuolla dongraida, nereden dongraida yerle? Uçurdun mu? Okay, sorry, just a second. Is it okay now?
Yeah, now it's okay.
Okay. So as a result, we get covariance matrix, and we found the reference point, and finally we project our covariance matrix to the tangent space, and we get the vector form of our initial EEG signals. And this vector form, we can use this vector form for the classification task. This is just the feature representation of our initial data. So for the classification task, we can use any classification methods. For example, the logistic regression, for example, on the target and non-target tasks, the binary classification, for example. And now let's move on to the PyRiemann library. Okay, this is a PyRiemann library, which is used to Romanian geometry. Okay, in the PyRiemann, this is an example of this pipeline of this task. For example, in the first step, we are finding the covariance of our initial signals. Then we are projecting our covariance matrix to the tangent space, and finally we are using just the classification, for example, logistic regression. And let's a bit dive into these steps. For example, the first step is estimating the covariance of our initial signal. We have some methods for estimating the covariance. The first one is just the normal covariance estimation. We have our data, x data with n epochs, x1, x2, and xn. And for each epoch, we will find the covariance estimation, but just the simple covariance. I mean, by using just a second, by using just these formulas, we'll calculate the covariance of our these epochs. I mean, in this function, the first one, the input as an input, our data, number of matrices, channels, and the time samples. Channel, okay, a multi-channel series. We have a lot, maybe 16, 20 channels. And as a transformation, we are just estimating the covariance of this time series, and our output will be the covariance of these inputs. Okay, it's almost in each slide we have links for deep knowledge. They are clickable. So the second method for calculating the covariance, I mean the estimating the covariance, is ERP covariance estimation. Okay, in that case, first we are the average. For example, we have some data already, xi. We are getting the average of this data, and we are concatenating with our xi data. And then after we get this super xi data, and after that we are calculating this covariance estimation for this super xi data. Sorry, it's just moved to the up. I will fix it. So this these methods can help us to get the temporal structure of our ERP data. Okay, temporal temporal structure of our data. It's better than this covariance estimation. In the last slides we will see the plus of these methods. And the next estimation for the covariance is X down covariance. Actually, this X down is a filter. I mean, before starting working, trying to find the covariance of our data, first we are filtering our data. We want to just focus on our ERP signal. We want to rid of our noise. For example, okay, this is our filter. Okay, our initial signal is equals, and with this filter W, we are filtering our data. And for example, how we are filtering? We have, just a second. First of all, we have our D matrix. This is a position of P300 components, P3 components of the signals. And with this one, we are finding our matrix A. Okay, then finding our A, the A is solution of this equation. Then after that we are finding our W, and then we are filtering our data. I mean, as I mentioned in here, it is maximize the just signal noise ratio, and it is reduce our features. Then after filtering with X down, by the way, in that case, we have a very detailed explanation of X down. I mean, So after we filtered our data, then we are applying this method. I mean the ERP covariance estimation. So as a result, okay, by these three methods, and with any of these ones, any of these three methods, we can take the covariance matrix of our data. So after we get covariance matrix, we will apply this tangent space, and this tangent space is, as I mentioned it before, just converting our covariance matrix to the vector forms in the tangent space. In that method, our input is this covariance matrix, number of covariance matrix, trials, channels, the dimension is. Then on the transformation part, first it's finding the reference point as I mentioned on the Riemannian geometry. First, finding by using geometric mean, finding the reference point. Then, by using this formula, it is converting our matrix to the vector form, and the result, our output is this projection on the tangent space. The shape is a number of trials, and the dimension of this vector, actually the dimension is n times n plus 1 by 2. The n is the dimension of the covariance matrix. Okay, after get the vector representation, I mean the feature representation of our signal, now our task is just classification. For the classification, as I mentioned in here, we can use logistic regression. Okay, and the final part, okay, this is our pipeline. Then, for example, in this plot, you can see that each method, for example, the green one, the best one is ERP covariance. First, for the covariance, we are using ERP covariance, then TS means tangent space, then the logistic regression. The best one is, and for each of these methods, it is explained in the right picture. LR, LVA, SVM, all of them are explained in this one. And also in this link, you can see the Vladislav's work. It's also using this PyRiemann library. You can read. It's a Medium post. You can read from there. And as a result, we talked about these steps: time series, Romanian geometry, PyRiemann library, and that's it. The best choice for classification of time series is the Romanian geometry, and that's it. Thanks for your attention. If you have any questions, I will try to answer it.
One question, please, about dimensions. The dimension of manifold and dimension of how it corresponds to channels or epochs and so on. How you choose dimension in this task?
Okay, just let me. Just a second. Okay, in this slide, the dimension of the manifold is, for example, if our this covariance matrix is n squared, the dimension of the manifold is n squared, and as I mentioned in here, for just a second. After we projected to the tangent space, the dimension of this vector will be n times n by 1 by n times n plus 1 by 2, the dimension of the vector representation of our covariance matrix.
And n is a number of channels or sample size, or what is n in this case?
N is a dimension of the covariance matrix. Just a
Yes.
second. Let me show you in here. For example, this is it is the dimension of the covariance matrix, and the dimension of the covariance matrix is, as you can see, the E. E is a electrodes. Put it on our brain.
So if we use 21 electrodes, we have 21 channels, and the dimension of manifold is n squared.
Yes, the covariance is 21, 21, and the representation will be 21 times 22 by 2, which means 11, 231.
Oh, thank you. Thank you very much.
Okay. Okay, as I mentioned in the beginning, I just introduced just in the brief introduction. There are a lot of linkable, clickable links. There are very useful links. You can read them. We'll post this presentation on the chats.
Yeah, I want to add that for particular problem of EEG signal classification, this is a really strong baseline, which is a good starting point. And yeah, well, as a conclusion, yeah, if you classify time series, it's good to give it a try, yeah, and to look how it goes. More than that, you could apply different types of this Riemannian geometry, like X down and ERP covariances and so on. So in fact, different regularization could give you better results in particular problems. So that's all from my side. Kerven, I think, do you have anything, or maybe someone? Okay, so if no additions, questions, then thank you for presenting. Thanks for coming, and see you next time. As I said, present your thesis here. This is a great experience for you before main thesis defense. Okay, so bye-bye. Thank you, Kerven.
Okay, thank you. Thank you for your attention. See you.